of my past projects, I was tasked to combine geography and mathematics within a project topic, which was frankly an absurd combination of subjects. However, after much pondering, I decided to investigate this through the tenets of seasonal lag. So for any aspiring IB students who want to sort of develop their IA or EE through a geographical sort of context, this could possibly be an unorthodox topic to sort of serve as an inspiration or a source or a starting point for you to develop your ideas into more complicated ones that will be suitable for a math IA or EE. So before we investigate this head on, it is important to understand the nature of seasons. Simply speaking, as the Earth rotates around the Sun on a tilted axis, one hemisphere is more directly exposed to the ray of the Sun than the other, increasing the insulation from the Sun's rays in comparison to the opposite hemisphere. This alternates as the Earth revolves in its orbit. In layman's terms, the northern hemisphere experiences maximum insolation from the Sun on the day of either June 20th or June 21st, which is known to us as the summer solstice. And therefore, ideally, the northern hemisphere should record the highest temperatures on that day because it receives the most insolation from the sun's rays at that moment. Conversely, the minimum insolation date, known as the winter solstice, is from December 20th or December 21st. Therefore, using a temperature curve of a northern hemisphere location, the graph should be something similar to this graph here shown on the right, with the maximum temperature around mid-June, as shown roughly here, and the minimum temperature around mid-December, which is shown roughly here, and therefore forming a largely symmetrical normal distribution as shown on the right. Now, I know what you might be thinking, that the temperature here might be lower than here. So this is actually a temperature graph of location in Russia, which is in the northern hemisphere, as a seasonal lag is present in every location within the world. There is no such thing as a location without any seasonal lag. This is just to illustrate that when a location has very minimum seasonal lag, it follows firstly the shape of a bell curve or normal distribution curve, and secondly that it is symmetrical, which means that if you integrate this curve over here from the limits of this to the middle of its domain, and you obtain the area below through this integration, and you compare it with the area obtained when you take the limits of the middle of the domain and the end of the domain, and you compare the two areas here and here together, which is separated by a line here, you find that that theoretically a place without any seasonal lag would have these two areas the same. And that the minimum temperature will be here and the maximum temperature will be here, which this graph largely but not accurately follows. However, we know that because seasonal lag is omnipresent within the world, it is defined as the phenomenon where the day of the maximum daily mean is delayed until sometime after the date of maximum radiation. So this can be shown within the graph over here, where if you cut the graph into two equal sections by domain, and you integrate this section of the graph using the limits from here to the middle of the domain, and you calculate the area here, and you do the same with the limits from here to here, you notice that between these two portions, this is significantly larger than this, and this represents the temperature curve in the northern hemisphere of a location with a very, very significant seasonal lag. Scientists propose that seasonal lag could be a direct consequence from close proximity to bodies of water, which has a high latent heat of condensation. Therefore, they absorb large proportions of the increase in insolation that comes with summer, and therefore aerial temperatures in these locations take longer to record this continued increase in insolation. This therefore causes this temperature graph to skew to the right, as shown as the peak has shifted from what originally was roughly in the middle of the domain to something significantly right of the domain. So in this investigation, we'll be investigating the relationship of the proximity of a body water to various locations in the northern hemisphere and the extent of seasonal lag, which can be displayed through the amount of skew and the difference in areas between the first half of the domain and the second half of the domain. The values of these domains, they represent the month number. So 2 will be February, 10 will be October, etc., etc. So therefore, we can conclude that an increased discrepancy between the two aforementioned areas represent increased skew of the temperature graph and therefore an increased seasonal lag, which we will reinforce later. For simplicity purposes, let's assume that the summer solstice is not June 20th, but we shift it very slightly, nearly negligibly, backwards to June 30th, and the winter solstice is not December 20th, but December 31st. Then the minimum temperature will be at the turn of the year, which will be the last bit of the domain. From graph of domain 0 to 12, this would be at the very last bit, and the highest temperatures should be recorded at exactly 6, which is the midpoint of the domain. This is assuming that there is absolutely no seasonal lag. So this means that if you integrate this curve between this limit and the middle limit and the midpoint of the entire domain, and you obtain the area A, and you do the same between the limits of 6 and 12, and you integrate this between these two limits, and you obtain the area, you notice that A and B are the same. So A and B shall be equal to 0, assuming that there is no skew to the right. The graph would thus follow a bell curve shape, or formerly known as a normal distribution curve, and would of course be symmetrical in shape as well. However, should there be seasonal lag, which is what we will be investigating subsequently, the graph will skew to the right, and the latter half of the year will experience highest temperatures, and B will be markedly larger than A, as shown right here. Because A is smaller than B, when you deduct B from A, you obviously get something from something less than 0, a negative number for any place which has a seasonal lag. Now, how do we quantify the extensiveness of the seasonal lag? Well, a seasonal lag will cause a graph to skew much more to the right than this. And when the graph is skewed much to the right of this, the difference between B and A will be much larger. B will be much larger than A, and therefore we can say that A minus B will be a greater negative number. As compared to a graph that is slightly skewed to the right, B will only be slightly larger than A, and we can put this in mathematical terms of A minus B will be a very small negative number. So the larger the difference between B and A, the larger the skew to the right, and therefore the more significant or extensive the seasonal lag is. So conclusively, the integration will be used to calculate the area underneath the curve from the first half of the year by setting the limits from 0 to 6 on the temperature curve. The integers represent basically the month of the year, so 10 will be August, 12 will be December, and this will be repeated for the second half of the year, and once these are both integrated and the areas of A and B will be calculated, they will be compared, and the difference in area underneath their respective limits is indicative of the extensiveness of the seasonal lag. Now, to keep all other factors constant, all 4 locations chosen are in the northern hemisphere. They all have a similar humid continental climate and similar temperature curves except for the extent of seasonal lag. The first location we chose is largely removed from any open body of water. The climate statistics in the form of mean monthly temperature of our first location, which is Moscow, is shown here. Moscow is far removed from any body of water, any significant body of water, and is 894 km from the nearest sea, large lake, or ocean. These data points are obtained from Wikipedia and are inputted into an interpolation calculator to derive a temperature curve for subsequent integration. And when you plug this into here, and when you plug the data points into this graph over here, this is represented graphically as shown here. So we can say that my interpolation machine or calculator is largely accurate as the graph largely follows the data points that we are given from Wikipedia. Now, to calculate the area underneath the temperature curve, we firstly use the limits of 0 and 6 to calculate area of A, which derives to be this. And we do the same for 12 to 6, which is the latter half of the year, and we obtain area B. So eventually we obtain a very small seasonal lag. However, we will compare this value with values of other locations which could be low, which are closer to a significant body of water. Now, these are the climate statistics of our second location in Bratislava, which is way closer to any body of water and is 380 kilometers from the nearest body. These data points are similarly inputted into an interpolation calculator for a temperature curve, as shown by the equation here, and is represented once again graphically here, showing that the equation is representative of the data points and therefore is accurate. Using integration, the areas of A and B are calculated, A being here, same limits for both A and B, and A is here, B is here. And when we do A minus B, we see that we obtain a larger negative number. Do pause to read the information and the integration procedure for this and the following examples as well. Now, these are the climate statistics for the third location, Jinan in China, which is only 186 kilometers from any body of water. The same process is repeated, once again represented graphically, very accurate. Plotline is interpolated from the data points that we have here, and we integrated using the same old limits, and we can see that when we take A minus B, we obtain an even larger negative number. And these are the climate statistics for our last location, Sapporo, which is basically adjacent from the nearest body of water, the Sea of Japan. So we obtained the equation as well. We represented via the graph, and our integration finds the differences between the areas of A and B, and a very large negative number indicates an extremely extensive seasonal lag. Also, another thing to note is without even comparing the area of A and B, we can obviously see that there is a skew much to the right, that the peak is like quite far from 6, 2 entire months behind 6, and even the minimum temperature is far behind where it's supposed to be, assuming that there is no seasonal lag. So we can see, based on merely the shape of the curve, that there is a very large skew to the right, and therefore that there is an enormous seasonal lag. So in conclusion, placing the differences between A and B for the 4 locations in the same table, we identify a very common correlation. So with a decrease in proximity, which means an increase in distance to the nearest body of water, we can see that the value of the negative sort of decreases. So we can conclude that the greater the proximity of a location to a body water, the larger differences in areas B and A, which indicate a temperature curve skewed more to the right, and therefore a larger seasonal lag. Therefore, we can conclude that the greater the proximity of a location to a larger body of water, the greater the seasonal lag. And this serves as our conclusion.